one of the ones which occurs very frequently in electrical engineering applications. Now, the equation of the Gaussian density function is that p of x, the density function, is 1 over the square root of 2 pi times sigma, which is one of the parameters of the density function, times e to the minus, now everything else is in the exponent. That should say x minus mu quantity squared divided by 2 sigma squared. If we could come in a little closer on this, I'd like to show you what some of the parameters might look like. Okay? You'll notice that the quantity mu, which occurs in the numerator of the exponent, now all this is in the exponent, the quantity mu, which occurs up here, is the location of the mean of the Gaussian density function, which in the particular case of the Gaussian function has 2 other important properties. The mean of the Gaussian is also the place where the density function has a peak. That's not generally true, but it is true in the case of a Gaussian density function. The other important statistic, which is sometimes used to describe the amount of clustering that a density function might have, is the so-called median. Now, the median of a density function is that point in which 50% of the area lies to the left of the point, and obviously 50% lies to the right. In the special case of a Gaussian, the mean is also the median. It's not generally true, but it's true for the Gaussian. The location of the peak of the density function is known as the mode, M-O-D-E, the mode. And in the case of a Gaussian, again, the mean is the same as the mode. This is also, I'll write this out, the median. Locate it right there. So we have the mean, the mode, and the median coincide at the point mu, where mu is the parameter that occurs in the numerator of the exponent. I've defined the terms just below here. Mu we'll call the mean. The quantity sigma squared, which occurs in the denominator of the exponent, is called the variance. And the quantity sigma is referred to as the standard deviation. You'll notice that the height of the Gaussian density function at the mode is 1 over square root of 2 pi sigma, because at the mode, or at the mean, x is equal to mu, so we have a 0 in the exponent, and the only value, p of mu, the only constant that's left, is 1 over square root of 2 pi sigma. So that's the height at the mode. If you went down to a point about approximately 60% of that value, which would be 0.6 divided by square root of 2 pi times sigma. The sigma is not inside the square root. 0.6 of the peak. Then going across here, the distance from the mean to the curve is approximately sigma, the standard deviation. So the standard deviation occurs in 2 important places. It's a measure of the spread of the Gaussian density function from the mean, and it is also inversely a measure of the height of the density function. The larger the variance, or the equivalently the standard deviation, since they're related so simply to each other, the larger the variance or the standard deviation, the lower this height will be, and the more spread out the curve will be. As we'll see when we discuss random signals, the Gaussian density function is the density function that is frequently used to model the random voltage or random current that one might observe in a random signal. And we'll see at that time that the variance is a measure of the power in the signal. The standard deviation then being a measure of the RMS value of a random signal. It's very important that you understand and know the form of this density function, and that you realize that the Gaussian density function is a two-parameter density function. That is, having specified mu and sigma, we have specified the entire density function. For that reason, a shorthand notation which is frequently used for the Gaussian density function is to just write capital N for a normal density function. Then in parentheses, you put the dummy variable, which may be little x, then a semicolon, and then the two parameters of the density function, mu and sigma squared. Having written this notation, that is equivalent to writing this equation over here, the equation for p of x in this line. They're equivalent ways of writing the same thing in that fashion. Let's just take a look at the Gaussian density function for a second and look at some of the bounds, some of the questions that we might ask. If we had a Gaussian random variable, one question that we might be interested in is what is the probability that the random variable lies in a range between some point m and another point m plus k sigma, where sigma is a standard deviation. Now k could be a fraction, so what we're really asking over here is the probability that x lies in a specified range. Well, from the properties of density functions, you can see that that probability can be computed by integrating the density function over the range m to m plus k sigma, integrating the density function dx. Substituting explicitly the value of the density function in there, you would obtain an integral from m to m plus k sigma of 1 over the square root of 2 pi times sigma. And then I use the notation for exponential function minus x minus mu quantity squared over 2 sigma squared. Whole thing integrated dx. Of course, the exponential function means that all this in the square brackets is in the exponent. I'll outline the square brackets a little heavier here so that you can see where they fall. Everything in the square brackets is in the exponent. And just by way of illustration, here's a little sketch to outline what this probability is that's being asked for. Here's an arbitrary Gaussian density function. There's the mean of the density function. Here's some arbitrary point m located right here. And here's the point m plus k sigma located right there. And we are asking to find this area. That area represents the probability that is asked for in this line right up here. Now, the integral that we have to evaluate is not an integral which can be evaluated in closed form. The integral can only be evaluated numerically. And as an aid to numerical evaluation of such integrals, we have defined something called a standard normal curve, which is defined in the following way. The phi of k is defined as 1 over the square root of 2 pi times the integral from 0 to k of e to the minus u squared over 2, integrated du. Now, u in this case is just a dummy variable, and this is a so-called standard normal curve because you'll notice that it's been normalized to 0 mean and a standard deviation or variance, which would normally appear down here and in the exponent, of 1. Now, the values of phi of k, which represent the shaded area, commonly known as the area under the standard normal curve, or in some cases it's related to another tabulated parameter known as an error function. The values of phi of k are tabulated in CRC tables or other tables, and it represents the shaded area right there. So our task in trying to evaluate an integral of the type that we had before, which was this integral here, our task is to make a substitution of variables to convert it to a standard normal curve in which we have the appropriate bounds and the appropriate limits on the integral. Let's try and do this. In the previous expression that we had before, make the following change of variables. Let u equal x minus mu over sigma. And having done that, you can verify that the limit of the integral goes from m minus mu over sigma to m minus mu over sigma plus k. And now if you looked at what area this would represent, you would see that the effect of this substitution has been to convert this area that we were looking for. It shifts the mean down to the origin so that we wind up with a zero mean curve, and it normalizes the distance measure so that we have a unity measure, and we would be looking for the distance from here to here. And if you compare that with what would be asked for in the standard normal, you'd see that it would be the distance to the upper limit minus the distance to the lower limit, so it would be phi of m plus k minus phi of m. A little juggling with the sketches will help convince you of that. This integral can be found from the tabulated standard normal integral. There's a special case, and that is the special case when m is equal to mu. When m is equal to mu, then what we're seeking, going back now to the original sketch, is we're looking at an area, if m were equal to mu, from the mean to the mean plus a certain number of standard deviations, somewhat like we had looked for when we were evaluating the Chebyshev bound in the previous tape. When that is the case, you can see that the limits on the integral, m minus mu becomes 0. M minus mu becomes 0 up top, which just leaves us with this plus k. And what we're left with then is an integral from 0 to k of 1 over square root of 2 pi e to the minus u squared over 2 du, which is by definition phi of k. So that what we have found is that the integral that we were asking for before, in the special case where we're looking for a certain number of standard deviations from the mean, turns into this tabulated function. In particular, if we double the range, so that we're asking for the probability that the distance, that's what these magnitude signs mean, the distance from x to mu, the probability that that distance is less than k standard deviations. In the case of a Gaussian density function, that turns out to be exactly twice phi of k. Now, phi of k is evaluated numerically, and therefore it is an approximation, but this equation is exact. Consequently, we can find something analogous to the Chebyshev bound that we looked at before for the special case of the Gaussian, except that it is a much tighter bound. Let me give you an example. If we were asking for the probability that the random variable would lie within one standard deviation of its mean, that would be reading this line across here. Looking at the sketch, that would be, here's the mean, that would be the mean plus one standard deviation, or the mean minus one standard deviation. we're asking for the probability that the random variable lies somewhere in this cross-hatched region, in there, plus or minus 1 standard deviation. The Chebyshev bound tells us that that probability is greater than 1 minus 1 over k squared, where k is 1. So therefore, the Chebyshev bound just tells us that that probability is greater than 0. Well, that's true, but not very informative. The exact value in the case of the Gaussian turns out to be 0.68. And that's a very important number to remember, because what it says is that a Gaussian random variable has a 68% chance of being within 1 standard deviation of its mean. Now, if you just recall for a second that I mentioned that the standard deviation will be related to the RMS value of a noise voltage, for example, what this says is that if you have a certain RMS value of noise and a certain mean value of the noise, that the Gaussian noise voltage will always be, or at least it'll have a 68% chance of being within 1 RMS unit of the mean. That means a good approximation to Gaussian noise is the mean value plus or minus its RMS value. That's a very good way of just thinking of random noise in that case. Gives you a very tight bound. Looking at the chart again, you can see that for k equals 2, you can just copy the number for k equals 1.5, but for k equals 2, the Chebyshev bound gives us a bound that the probability is greater than 0.75. The exact value is 96%, 0.96. And now looking down at that sketch, 2 standard deviations is now the overall shaded region, as I've just done over there. And it says that in the case of a Gaussian random variable, we have a 96% chance that the random variable lies within 2 standard deviations of the mean. And by the time you get to 2.5 standard deviations, which would be adding just a little bit over here and a half a standard deviation on this side as well, it's a 99% chance. I think you would agree that for all practical purposes, a Gaussian random variable lies within 2.5 standard deviations of its mean, and frankly, it lies in general within 2 standard deviations of its mean. We're only losing 4% of the area, as you can see here, which would be 2% on either side, by truncating a Gaussian density function at 2 standard deviations from the mean. Okay, now why is the Gaussian density function so important? Well, the primary reason for this importance is the so-called central limit theorem. Now, central limit theorem is one of these theorems that has been stated a number of times, and mathematicians are continually working on ways of generalizing the theorem somewhat. The theorem states the following. It says that if we have a set of random variables, capital X1, X2, and so forth, up to capital Xn, and that these random variables are statistically independent, that's an important condition, that the random variables are statistically independent, and that these random variables have themselves arbitrary density functions. You can have any density function at all. It doesn't matter what their individual density functions are, except that each of them should have finite variance. It means they have finite power. That is a restriction which we add. Then if I form a new random variable, y sub n, which is formed by summing from I equals 1 to n the x's. In other words, I just sum up these x's. Then the following is a fact. As n becomes large, the random variable yn, that is the sum of these random variates, becomes Gaussian. And that is a very important result. It says that if you just sum up an arbitrary random set of random variables or arbitrary random variables, you add them all up, then if you add enough of them, the sum will be Gaussian. Now, the reason that that is such an important theorem, the central limit theorem, is that there are many operations that occur in engineering which are in fact summation type operations. One of the most important examples of this is in the case of the response of a linear system, because you remember the response of a linear system is the convolution, which is a type of summation operation. So that what the central limit theorem would state would be if you put in virtually any type of noise voltage into a linear system, that over a period of time, if you allowed it to run long enough, the result would be Gaussian. That's one example. Another example which I could show you would be the following. Let's look at this, just a sketch for a second over here. If we had a vacuum tube, for example, all I'm showing over here is just a plate that would be positively charged, and we'll heat a cathode underneath the tube so that electrons will boil off the cathode and migrate to in this direction towards the plate. Then look at the voltage that we would observe over here if we connected a meter. We connect the meter to this point, say voltmeter. The voltage that we'll observe will be the effect of all of these electrons hitting the plate. Be the sum of the electron potentials of each of these electrons hitting this plate. That will be the voltage we'll observe. Actually, the voltage that we'll observe, of course, will be plus to minus in that direction, because when an electron hits the upper plate, it will effectively render a net negative charge. But be that as it may, we'll measure a voltage here, and the more electrons that hit the plate, the higher the voltage will be. The fewer electrons that hit the plate, the lower the voltage will be. But the overall voltage will be a composite of all these electrons striking it. Each of these electrons, the question of whether or not it strikes the plate, is a statistically independent event. Statistically independent, because this electron doesn't know what that electron's doing. All right? So that what we're looking at, the voltage that we would observe over here, V of t, is a composite, a sum of a bunch of statistically independent random variables. How many? Well, it would not be uncommon for 10 to the 15, 10 to the 18, 10 to the 20 electrons to be striking that plate. Certainly a large number, and therefore the central limit theorem would certainly apply. And the central limit theorem would tell you that the voltage that you will observe over here, V of t, is Gaussian. This, by the way, is an example of something called thermal noise. Because the noise is created, actually in this case we have something which is perhaps more correctly called shot noise, noise which is comprised of a bunch of individual electrons striking the plate like shot. The mechanism by which these electrons boil off is a thermal mechanism. Both shot noise and thermal noise we generally expect to be Gaussian. Okay. Another important density function is the so-called binomial distribution. Now, the binomial distribution has application whenever you have binary events. That is, the only possible outcomes of a random experiment are the events A and A complement. In a binary communication system, for example, one might transmit the channel symbols 0 or 1 as possibilities. That would be a binomial type situation. Furthermore, we specify the probability of the event A is P, and the probability of the complementary event, A complement, is 1 minus P, or Q. Now, the question is, if we repeat the transmission of this, we repeat the experiment n times, what is the probability that we will have m occurrences of the outcome A? That probability is governed by the binomial distribution, and it is given by the symbol that we use as P sub n of m. M is the number of outcomes we're trying to find the probability of. N is the total number of repetitions of the experiment. The terms here are the number of combinations, C super n sub m, the number of combinations of n things taken m at a time, times p to the m. P is the probability of the event A. Q to the n minus m, where Q is the probability of the event A complement. And the so-called binomial coefficient, C super n sub m, just called for short CNM, is given by n factorial divided by n minus m factorial times m factorial. Recall in doing some of these combination or evaluation of these binomial coefficients, recall please that 0 factorial is equal to 1, because 0 factorial is one of these things that will arise frequently. Let me give you an illustration of how this might work. For an illustration, we're going to send 5 binary symbols down a channel, down a communication channel. The binary symbols will be either the symbol 0 or 1. The probability that we'll send a 0 is 0.6. The probability that we'll send a 1 is 0.4. Question is, what is the probability that we will have 3 zeros in 5 message symbols? All right. Now, we could apply the binomial formula directly, but I just want to show you where that formula comes from. One possible favorable outcome is the following. We could have the 3 zeros first, followed by 2 ones. The probability that we would get that outcome is the probability that we would have a 0 times the probability we'd have a 0 times the probability we'd have a 0, which is 0.6 to the 3rd power. The probability that we'll have a 1 followed by a 1 is 0.4 squared, 0.4 to the 2nd power. And the probability that all of these things would happen is just the product of the probabilities. So this is the probability of just one possible outcome. Now, how many such outcomes are there which are favorable outcomes? Well, another possible favorable outcome, which I'll write over at the side, would be 0, 0, 1, 0, 1, for example. Notice that that's a combination of the event that I'd specified the first time. It's a combination. Notice that we would not apply the laws of permutation here, because in a permutation we would get a different ordering if I interchange these 2 ones or if I interchange these 3 zeros. And that of course is not a different ordering. We can't distinguish between the zeros and we can't distinguish between the ones. So it's a combination. And the number of combinations of 5 things taken 3 at a time is 10. So therefore, applying the binomial formula in this case, what it does is we take the probability of one event and multiply it by the number of possible events we could have obtained. In this case, it turns out to be 10 times 0.6 cubed times 0.4 squared, which turns out to be 0.35. The binomial distribution is called a distribution, but in fact, it's technically not a distribution. It's certainly not a distribution in the sense of the distribution function, and it's not really even a density function. It's just given this name, but really what you're getting is a probability, and it is a discrete probability. I think it should be clear to you that the sum, if I take a sum from I equals 0 to n of the probability of I successes in n tries, that sum has to be 1.